All right, so this today's topic is definite integrals and numeric integration. So this is where we're starting to get into the idea of, all right, let's go back, let's compare it to something that we already know. So at the end of the day, what is the derivative? What does it represent? Not how to do it, but what is it? So hopefully you said something along the lines of the slope of the tangent line, right? So that's what's represented by the derivative. The integral is a different representation. It's the area underneath the curve. So the integral is this space. Now, this is a tough problem in mathematics because similar to when we did the derivative of the tangent line only has 1 point. So how do you figure out the slope when you only have 1 point? We're in the same boat here. How do we find the area underneath this curve when we have such a weird shape? You know, if this is just a rectangle, hey, life would be good, right? Or a square, or even a triangle, any sort of shape that we are comfortable with. But once we get into this curviness, things get kind of tough. So, all right, so going back to, let's start off with what Corpy's talking about here, kind of what I just said. First, we figure out what the instantaneous rate of change is. That was the derivative. So that's why this is called the calculus, because it's the merging of these two different calculi. The first one is the differentiable calculus, derivatives, and then the integrable calculus, which is integration. All right, so how do we find the area of these irregular regions? Well, let's do a quick review of how summation notation works. Remember, this is capital sigma. This is the index. This is the number that you start plugging in first, and you keep plugging in consecutive numbers until you get to the top. So, for instance, if I wanted to figure out the sum of I squared from I equals 1 to 3, now there is a formula. I don't know if you remember it from pre-calc. I had to look it up. I didn't remember it, but there is a formula for it. Since this is so small, it's easier to just plug and chug and calculate. So I plug in 1, 1 squared is 1, plus, because it's a sum. Then I plug in 2, 2 squared is 4, plus, because it's a sum, 3 squared is 9, that's 10, that's 14. All right, I'm going to pause, have you try to do this one on your own. All right, let's see how you did. So I'm going to plug in this time. My first value is 0. So I'm going to plug in 0, 0 plus 1. Sorry about that. Okay, so I'm plugging in 0 for n. Just leave x as it is. Don't be intimidated by that x. It's just x. We don't know any values for x. So the best we can do is leave x as x. I put 0. 0 plus 1 is 1 over 2 to the 0th. Remember, I'm plugging in the 0th term. Then I'm plugging in 1. So 1 plus 1 is 2. Plug in 1. That's 2 to the first. Plug in 2. 2 plus 2 is 3. 2 to the second. Plug in 4, 0, 1, 2. Plug in 3 next. 3 plus is 4. 2 to the third. Plug in 4 plus 1 is 5. Oh, I'm running out of room. Over 2 to the fourth, plus x to the sixth, over 2 to the fifth. That makes sense because when I plugged in 0, 0 was my first term. So to get to 5, I should have 6 terms. 1, 2, 3, 4, 5, 6. Let's clean this up just to make ourselves feel a little bit better. 2 to the 0th, that everybody knows, is 1. So x to the 1 over 1 is just x. Plus x squared over 2 plus x cubed over 4 plus x to the fourth over 8 plus x to the fifth over 16 plus x to the sixth over 32. All right, so how did we figure this out? How did mathematicians come along and figure this thing out? We will now approximate the irregular area. Now notice that key word there. Let's highlight that. We're going to just approximate for now. Approximate that area. And so how did mathematicians come up with this? Well, they came up with the idea. Riemann is the one who's famous for it. Bernard, it's later in the notes here. But he came up with this idea as, well, let's take this thing and let's divide it into little rectangles. Now, we can take this and divide it into rectangles that are easy to find the area, but it's always going to be an estimate. We're not going to do a great job. So we have these different kinds of estimates. So you can do what's called a left-hand estimate, a right-hand estimate, a midpoint estimate, or a trapezoid estimate. Okay, so like I said, we are going to approximate this area by making little rectangles. So I'm going to take this, let's say we decide to divide this into 4 equal sections. So let's say I'll cut it down the half, cut it half and half again. So I'm going to then take the function value at this, using the left side. So at this interval has a left end, a right end, as a midpoint, and then this trapezoid rule that we'll talk about. So the first one that I want to talk about, let's get a different color, is the left hand estimate with 4 sub intervals. All right, so I would take these intervals. I'm using the left edge, so I would go from here up to there. And then I'm using the left edge, so I would go here. Actually, I'm going to draw this one in there. So this would be my first rectangle. Then I would use the left edge. Then I would use the left edge. I go wherever the height of the function is, or the y value of the function. And then I would use my area formula of a rectangle. I could figure those out, add those together. Now, as you can see, this is not a very good estimate, right? These are way, way over what it is. And this one kind of comes out nice because this kind of cancels each other a little bit over here, but a little bit under there. That one's way under. So, you could get the idea that it could get us fairly close. So that's an example of a left-hand estimate. Let's do a right-hand estimate. Let's do that in blue. With 4 subintervals. So this time I'm taking my interval, my subinterval, and I'm starting on the right-hand side and I'm going up to the function. So now I'm going here and then I'm working backwards because this now is the right side. This is the right end of it. So I would use this. I would go up to here. I would go up to here. Now here we got this one's a real underestimate. This one's over. This one's a little this one's an overestimate. This one's an underestimate, but the idea is it gets us close. So the other 2 styles, we have what's called the midpoint. The midpoint estimate. With 4 subintervals. So now I'm going to go in my interval and I'm going to find the midpoint. I'm going to track that up to the function there, and then I'm going to use that function value as the height of my rectangle. So there's my rectangle here. I take the midpoint, I track up to the function, I use that. Dang it, I wish I wouldn't have drawn that there, but I did. Then this one here, there, here. There's my rectangle now. And the midpoint's a pretty good estimate because you're usually a little bit over on one side, a little bit under on the other side. So it kind of balances out back to pretty close to what the actual area is. And then the best one, the one that we use the most, is called the trapezoid rule. I'm actually going to do this in black so it's easier to see. The trapezoid estimate with 4 subintervals. All right, so the trapezoid, remember our trapezoid is has 2 sets, or one pair of parallel sides. So I'm going to use the left-hand estimate as one side, the right-hand estimate as the other, and then I'm going to draw a trapezoid in there. Now this one's slightly over, but that's a pretty darn good estimate. It's not as bad as the right hand or left hand estimate. So I'm going to use the left hand, the right hand, and I'm going to turn that into a trapezoid. I'm going to use the left hand, I'm going to use the right hand, I'm going to turn that into a trapezoid. I'm going to use the left hand, I'm going to use the right hand, I'm going to turn that into a trapezoid, and I would calculate the areas there. So these are the 4 different ways that we're going to try to calculate areas underneath the curves. All right, so to actually do an example here. So we're going to do another 4 subintervals of equal width. That's going to be nice. That equal width thing is going to come into play later on. When you don't have equal widths, it's a little bit more complicated. Not too bad. But we're using the function x squared. So luckily Corpy already graphed it for us from 0 to 1. So we're trying to find the area of this region, and they'll usually highlight it in like shaded in, and then use some sort of capital letter to indicate the area that they're talking about. So we want to do this using a left endpoint, a right endpoint, midpoint formula, trapezoids, and then I'm going to show you how to do it on your calc as well. So let's start off with doing the left-hand endpoint. Now, before we can do any of these, actually, I should have done this first, is we need to divide this into 4 equal subintervals. So let's take, I'm going to do it in gray. So this interval is a length of 1. I want to divide it into 4 equal sections. I draw the middle one first, and then I can draw those next 2. Gives me a pretty good estimate of breaking that down. Now, if I divided 1 into 4 equal sections, how big is each gap? How much is each one of these tick marks? You can fill that in on your own. All right, let's see how you did. Well, halfway to 1 is 1/2. Halfway to 1/2 is 1/4. And then 1/4 and 1/4 and 1/4, that gives me 3/4. And then a gap of 1. So let's start off. I'm going to do the underestimate in pink. Sorry, the underestimate. The left endpoint is I'm going to do in pink. So I'm going to start with my interval. I'm going to go to the left end of it. So there's the left end. And then I go up to the height of the function. The height of the function is 0, and I would draw a cross. So this is not a very interesting rectangle, but that's the function that we have. So now I'm going to go to the next interval. I'm going to go to the left side. I'm going to track up to the curve, and as soon as I hit the curve, I'm going to use that height as the height of my rectangle. Then I'm going to go to my next interval. I'm going to go to the left end of it. I'm going to track up. That's going to be the height of my rectangle, and then I'm going to use the left end, track up to the curve. Now you can see right off the bat that in this case we ended up with a the left endpoint estimate is definitely going to be a underestimate, and that makes sense because in this interval from 0 to 1, what's happening to my function x squared? It's increasing. So if I start on the left side of it, I'm always going to have the lower points. So when you have an increasing function, I want to change my color because this isn't always, and left endpoints aren't always underestimates. It just depends. So when you have an increasing function, the left endpoint is always going to be an underestimate. And if you were to do, and we're going to show that in a second, but you're going to see that the right hand is going to be an overestimate. Now we might as well put this in here right now. We don't have a decreasing function, but you could kind of picture that if we did it on the other side of the y-axis there. If you have a decreasing function, the left endpoints will be an overestimate because that'll be the high side because then it goes down from there. And the right side would become the underestimate. Okay, so let's go back and finish this left endpoint approximation. So I'm going to calculate now. The height is given by the function value. Remember, I'm going to the left end and then I'm tracing up to the function. So at this spot, my x value is 0. My function value would then be f of 0. Multiplied by this rectangle's area is going to be its height multiplied by its width. Well, the height is the function value and the width is the length of the interval. So in this case, that would be 1/4. Plus, I move on to my next interval. This interval's height is this y value. That's the y value. That's the function value at 1/4 multiplied by a width of 1/4 plus the function value at 1/2 multiplied by, how big is this interval? It's 1/4 again. Plus, how tall is that function? It's the function value at 3/4 multiplied by 1/4 again. Oop, I didn't need that. Okay, so let's clean this up. What's f of 0? Well, that's 0. Now let's go over here and do that. I like it over here. So f of 0 is a height of 0. So that would be 0 times 1/4 plus, what's f of 1/4? Well, 1/4 squared is 1/16 times another 1/4 plus, what's my function value at 1/2? So I'd plug in 1/2 into squared. 1/2 squared is 1/4 times my width of 1/4. Then 3/4 squared, so that's the 3 and the 4 get squared, so that's 9/16 times 1/4, which ends up being, that's 0, plus 1/64 plus 1/16 plus 9/64. Let's shoot for a common denominator here. So yeah, I'm going to just rewrite it. I don't feel like rewriting that whole thing. So if I want to make this a common denominator, I need to make this a 4 and this is 64. So now I've got a common denominator. 1 plus 4 plus 9 is 1014 over 64, which of course reduces to be 7 over 32. And we said that this was going to be an underestimate because f is an increasing function on the interval 0 to 1. Now, this gets pretty tedious if you want to write out every single step. So let me show you a little shortcut. There's always tricks along the way. What do you notice this term has? A fourth, a fourth, a fourth, a fourth. Now, what you can only do this if you have an intervals that are subintervals that are the same length. But I can rewrite this thing. I can take the 1/4 out of all of it, and then I can find the function values at each spot. F of 0, f of 1/4, f of 1/2, f of 3/4. Then I could plug and chug. It saves you a little bit of time, so you don't have to keep writing that 1/4 over and over and over again. So I'm going to encourage you to pause here. Go ahead and pause and see if you can figure out how to do this with the right endpoint. All right, let's see how you did. I'm going to use a light blue here. So now I'm going to use the right end of the interval. So I go to the right end of the interval. I track up to the function. That's going to be the height of my rectangle. I go to the right end of the interval. I track up to the function. That's going to be the right end. I go to the right end. I track up to the function. That's going to be the height of my rectangle. I go to the right end. I track up to the function. That's going to be the height of my rectangle. All right, like we said, I mean, we already talked about this, but that's definitely, this is an increasing function, and we're using now a right-hand estimate. So these are going to be all over estimates because the right side's always going to be bigger than the left side. So I've got my same interval of 1/4. My first function height, though, isn't 0 this time. This time, this height, the height of this rectangle is f of 1/4 plus f of 1/2 plus f of 3/4 plus f of 1, which equals 1/4 times f of 1/4 is 1/16 plus 1/2 was 1/4, 3/4 was 9/16, and f of 1 is 1. I'm going to combine these first. 1/4, 1/6. Let's go ahead and just do it. So I need a common denominator, so I'm going to make this a 4 and a 16. Need a common denominator, so I'm going to make that a 16 and a 16. So what do we got here? 9, 10, 26, 30. 30 sixteenths, which ends up being 30 64ths, which ends up being 15 32nds. This is a over estimate. Well, see if you can do it now without my help. You and your friend, hopefully you were doing it, studying with your mathlete, your math buddy. Let's see if you can do it with a midpoint. All right, let's see how you did. I guess I'll go with yellow, I guess. All right, so yet again, how far is my interval? 1/4. So I've got the common interval. Now what I need to figure out here is what am I looking at for the height of my rectangle. So now I'm going to the middle, and that's going to be the height of my rectangle. I go to the middle, track up to the function, that's going to be the height of my rectangle. Go to the middle, track up to the function, it's going to be the height of my rectangle. Middle, track up to the function, that's going to be the height of my rectangle. So my function, my rectangle heights are going to be the function values at the midpoint. So the midpoint here, that's 1/8. So that's 1/8, 2/8. This is 3/8, 4/8, 5/8. 6/8 reduces, 7/8, then 8/8. So I'm going to do f of 1/8 plus f of 3/8 plus f of 5/8 plus f of 7/8. Got my 1/4 out there, so I'm doing 1/8, that's 1/64th, plus 3, that's 9/64ths, plus 5, that's 25/64ths. That's 7, that's 49/64ths, which is 1/4 times, oh nice, All right, I'm going to give that 1 to that one, that makes it a 50, that makes it a 75, I'm going to make that a 10, it's going to make it an 85, but I'm going to take one back, so that's 84 64ths. Let's see if we can, I don't want to do that, I want to reduce this first. Does 4, yeah, 4 goes into both of those, so that's 21 over 64. Anything reduced? Oh my gosh. Sorry. God darn it. All right. Hopefully that reduces. No. 3, 7. Nope. So this is it. Now this is neither an overestimate or an underestimate. I mean, it's going to be one or the other. Sorry, but we can't tell what it's going to be if it's an over or an under yet. All right. So trapezoid rules. Let's remember what a trapezoid looks like. We drew it on the front, but just a reminder, what would be a good, maybe like a green. Okay, so a trapezoid looks something like this. Or something like this, depending on which function value is higher on the left or on the right. We call this the height, believe it or not. Usually trapezoids are drawn like this, if you remember back to elementary school. This is the height, so this would be the height, and we call this B1 and we call this B2. This would be B1 and B2. All right, pause, see if you can remember how to calculate the area of a trapezoid. All right, let's see how you did. So let's come back up to the top. Area of a trapezoid. This is one that they don't give you. You got to memorize this one. So here's how I figured it out. I mean, this is what made sense to me when I thought about it this way. So I'm going to take our trapezoid again. All right, now from here, I'm going to take that exact shape. I'm going to double it. I'm going to copy it, and I'm going to flip it over. So I'm going to take this thing. I'm going to rotate it 180 degrees. And attach it. Now, what shape do we have? We have a rectangle. Now, remember our identifiers down here. This was called the height. This was called base 1. This was called base 2. Well, once I rotate it, what's this? The height. This is base 2, and this is base 1. So if I said calculate the area of this rectangle, your area would be height times base 1 plus base 2. The problem is we don't want the full rectangle. We want half of that. So we literally take this formula for the rectangle and cut it in half. So the trapezoid area formula is 1/2 height times base 1 plus base 2. If you want to call this base and this height 1 and height 2, I don't, whatever. Whatever. You do you. All right, so coming back to our situation here, I now need to take these intervals and I need to make them into trapezoids. So I think we're going with green. So I take the left endpoint, I take the right endpoint, and I make a trapezoid. Left endpoint, right endpoint, I make a trapezoid. See how much closer this is to what the curve is actually doing? So these are going to be really good estimates. All right, now each one of these trapezoids has what kind of a height? Each one of these gaps is still going to be 1/4. So I'm going to take out that 1/4, and I'm going to go brackets at this spot. I actually kind of wish I would have done brackets up above, but I'm going to do brackets now. So my area formula is I need to do a 1/2 out in front of the whole thing as well, don't I? I'm going to start over. So I need to do the 1/2 that's out in front for my base formula. It's 1/2. My heights are all going to be 1/4 times by 1/4. That's I call it height. Times by the quantity. All right, now I'm going to do each base 1 and base 2 for each one of these rectangles. So my first base 1 and base 2 is, let's go back to green. So that's f of 0 plus f of 1/4 plus, this is going to be really annoying, f of 1/4 plus f of 1/2 plus f of 1/2 plus f of 3/4 plus f of 3/4 plus f of 1. I don't want to calculate that. I mean, we could, right? Let's just, oh, dang it. I got to keep looking up at the screen. I keep looking at the paper. So hopefully, there you go. You could calculate that. I'm not going to spend time. How big of a pain would it be? Yeah, it'd be a pain. So you could calculate that on your own. That's your assignment. All right, now let's use our calculator to do this integration graphically. So I'll grab a calc. So I want to now calculate this function, x squared, I'm going to do a nice window. So I'm going to adjust my window from, let's say, negative 0.5 to 1.5 so that we see our region. I'm going to go from negative 0.5 to 1.5 as well. And so we get a pretty good picture here. So there's my interval, which is the same as what they've sectioned off. Now, our calc has all sorts of nice tricks, man, and everything's underneath calc here. So everything good on this screen when you're trying to just type stuff in is underneath math. That's all your good stuff there. But when you're in your grapher, everything good is underneath calc. So we want to go down and we have this integrate button. Now this is nice. This is what you would call a definite integral. It gives you a boundary. So this is a beginning and an end. If you remember the last time's notes, we just did derivative or integrals, right? We just integrated things and we always had to put that plus c at the end. Those were indefinite integrals. These are definite integrals. So where I'm going to select the integration option, it's going to say the lower limit. That means what's the left end of the whole interval? And for us, that's 0. What's the right end? 1. And be prepared to be dazzled here. It actually shades in that whole section and it calculates what that area is. Now, you know how AP is. You don't get to use a calc on every single problem, but when you do get to use your calculator, don't waste time trying to integrate by hand. Go right to your grapher and integrate. So actually, this is also, by the way, underneath alpha F2 function integrate, we would go from 0 to 1 of x squared of integrating according to x, so we'd get the same number. What's nice about that, you could frac it back. I hope you know that 0.3 repeating is a third, but it's another way to do it. All right, anyway, so what does that mean? That means that the total shaded area is 1/3. Now, how were our estimates? Let's go back and just kind of estimate these. So let's see how 7/32, 0.2, that's approximately 0. No, it's equal to. We got to do that fancy equal to. We're going to talk about when to use approximately and when not to. 0.218. Like we said, that's an underestimate. 15/32. That's equal to 0.468. Like we said, that's an overestimate. 21/64. Well, this one ended up being a little bit of an underestimate. Look at how much nicer that value is, how much closer it is to the actual number. And then whatever that was. Oh, geez. I'm real tempted to actually calculate it. I'm going to pause and calculate it and just tell you what it is. All right, so I calculated. This ended up being, oh boy, 11/32, which has a decimal value of 0.343. Is that closer? No, this one's actually closer, isn't it? Yeah, that's interesting. So usually trapezoid is your best one, but in this case, the midpoint was. So using our calculator's numeric integration capability, there was 2 ways to do it. Remember, you could graph, then do second calc, then what did that look like? Then use integrate f of x dx. Or the other option was go to the main screen and do alpha F2. So that's when I went alpha. I can get back here, clear, clear, clear. Alpha F2, and I went down and selected function integrate. And then you would put in your boundaries. You would put in 0 to 1 of your equation dx. Both of them are going to give you the same place.